Okay? Key phrases here: momentary, partial. Right? That momentary means fractions of a second. Partial charge, so it's not a complete charge, so it's not going to be a strong charge. Okay? So what happens is, if I got H2, H2 is nonpolar, because the two H's pull evenly. Okay? So how is H2 going to stick together as a liquid? Well, for a fraction of a second, the electrons on one molecule are going to move to one side. If they're randomly arranged, randomly they're going to show up more on one side than on the other. When that happens, this molecule is going to affect the electrons in that molecule. So the negative charge on that end is going to push the electrons away from this end. And those electrons will be pushed away. And when they're pushed away, I now have a negative next to a positive. So those two molecules would stick to each other. That's dispersion forces. As long as you have electrons, this can happen. Every molecule with electrons, this happens. So what kind of molecules do this? Well, all of them. Okay? But it's the only thing that happens when there's nonpolar molecules. So, dispersion forces. The strength of the dispersion force depends on the number of electrons. I've got a little minor issue with your book. It doesn't show, it's not a big deal, but your book says with the size of the molecule. But it's actually not the size. It's how many electrons there are. It just so happens that if you have more electrons, you're a bigger atom. But it's not the size that makes it happen, it's the electrons. The more electrons you can move around, the easier this is going to be to do. So bigger molecules have more electrons. So bigger molecules are going to stick together better. So the more electrons I have, the stronger the force is going to be. The stronger the force, the better they stick together. The better they stick together, the less able they are to make that change we talked about, going from a liquid to a gas. So on my periodic table, it's color-coded. And if we look at the halogens, we said the halogens were always diatomic. F2, Cl2, I2, Br2. Right? Those are all diatomic. But on my periodic table, they're color-coded by states of matter. Okay? Fluorine is a gas because it can't do dipole interactions because it's not polar. So it can do dispersion forces, but it only has, F2 only has 18 electrons to do it with. And 18 electrons is not going to do it very well, so F2 doesn't stick together very well. F2 is a gas in this room. Br2. Br is number 35. So in Br2, it's still nonpolar, but now it's 70 electrons, not 18. 70 electrons can move around more. 70 electrons can do dispersion forces better. 70 electrons is going to stick together better. So in this room, bromine's a liquid. It stick together so well that it can't escape. This is at room temperature. If I heat it up, I can turn bromine into a gas. If I cool it down, okay, because temperature has to do with the motion of the particles. So the less I get the particles moving, the better they're going to stick together. Okay. And then iodine's a solid. Because iodine, its dispersion forces are going with 106 electrons, 53 apiece. So notice I'm not talking about just the valence electrons. All the electrons can do this. Okay? The one in the middle is too much on one side. That gives that side a negative charge. So the more electrons, the better they can do this. So, okay, another place it shows up, okay, fossil fuels. All the stuff we burn to get our energy. Okay, so the natural gas, they're all hydrocarbons. Oops, sorry. They're all hydrocarbons. And hydrocarbons means that they have just carbon and hydrogen. Okay. CH4, well, first of all, they're all going to be symmetrical. They're all tetrahedrals. And C and H, the electronegativity difference is 0.4, which is too small to be polar. So if it's made up of just C and H, it's nonpolar because the difference is 0.4, which is too small. So all of these are going to be nonpolar. CH4 is natural gas, methane. The stuff that comes out of the stove, the stuff that lights a Bunsen burner, that's CH4. It's a gas. It's a gas because it only has 6 and 4, 10 electrons that can do this. 1 for each hydrogen, 6 for the carbon. Not valence electrons, total electrons. Okay. Now, C3H8 is propane. Anybody use propane at home? For the grill, right? Got a propane tank that hooks onto your grill or onto your patio heater. That tank is full of liquid propane. But as soon as you let the pressure off, it turns straight into a gas. As long as I keep the pressure high, it stays a liquid, but if I let the pressure off, it turns into a gas. Yeah. CH4 is methane. Methane, that's the natural gas, the stuff that we use in our Bunsen burners. Okay. Propane's a liquid if it's under high pressure. Okay. Butane is C4H8, and C4H8 comes in a handy little container. Oops. Got some over here. Okay. Inside a lighter, there's a liquid. But if you push the button, the gas comes out. That means this stuff is boiling, right? So under pressure, it's a liquid. Let the pressure off, it's a gas. But I don't need nearly the pressure for this that I need for propane, because I can do this in a piece of plastic. With propane, I need a big metal tank. So propane needs higher pressure to stay liquid. This, with a fairly low pressure, can stay liquid. So this sticks together better. Why does this stick together better? It sticks together better because it's got 24 and 8, 32 electrons to it, versus 18 and 8. That makes a difference. When I get to C5H12, C5H12 is a liquid. So by the time I get to C5H12, it's big enough it's going to stick together and stay a liquid in this room. Everything from C5 all the way up to about C16 is a liquid. You may know of them, C8, H18, that is octane. So they're measuring octane, they're measuring how much C8, H18 is in your gasoline. Gasoline is a mixture of different ones. Octane is C8, H18. Still liquid. Still liquid that evaporates pretty easily. Right? Gasoline evaporates faster than water, right? So it comes from fairly easy. Now, once you get to about C17, you get wax, a solid. So if it gets big enough, this force is strong enough to keep it a solid. So waxes are carbon and hydrogen with big molecules. They stick together. Propane and butane, middle-sized molecules, they stick together a little bit, but they don't stick as well because they don't have as many electrons. So that's one place you see it. One of the cool places you see dispersion forces is this. Okay, that's a gecko on a piece of glass, upside down. There's a piece of glass on the ceiling. The gecko is walking across the ceiling, upside down. The gecko can hold its entire body weight with one paw on a piece of glass. Okay? And the paws aren't sticky. They're perfectly dry. There's no sticky substance on them. They don't leave footprints behind when they walk across the glass. There's nothing on their feet that makes this, that comes off that's like a glue would be. So what makes the gecko stick? Okay? Well, if you look at their foot, their foot has a whole bunch of little tiny hairs on their toe. And those little tiny hairs have little tiny ends. And those little tiny ends have little tiny knobs. And those little tiny knobs touch the glass. And the electrons are not evenly distributed in those little tiny knobs at any given time. So they move the electrons around in the glass just like the balloons move the electrons around in the wall. And it's dispersion forces that let a gecko hang by its foot. And its key is it's got lots of surface area to do it. It's touching molecule by molecule all across the surface because those hairs are so fine. Okay? So, well, no, not even magnets, because magnets would be permanent. Just the random motion of the electrons at the end of those hairs changes the glass so that they have opposite charges and the gecko can hang on.
So they got hairy hands.
Got hairy hands, hairy fingers. Okay, it's also the same thing.
When the balloon stuck to the wall.
So it stuck to the wall, except yeah. But balloon was permanently charged. This is just a fraction of a second. It's uneven at the end of that paw. It's not a permanent charge. It's a temporary partial charge, just like the hydrogen did, except enough to hold a gecko hanging from a ceiling. Okay? Once they noticed this, they decided, hey, we should make tape like this. Because if you're taping electronics, you don't want to leave a residue behind. So now they're manufacturing tape that you put on and off without a residue. It's expensive tape, but in lots of applications, you need something that doesn't leave a residue once you've hooked it on. You ever had to, you watch me pass out papers, and I don't even bother to count because the papers stick together so well. Why do the papers stick together so well? Dispersion forces. All the electrons on the one piece of paper are not evenly distributed, so they're going to affect the piece of paper below it. That's what keeps two pieces of paper stuck to each other, even though neither one has a charge. And most of you have experienced that. Right? So it has some real impacts. Now, you have to get a lot of surface area. See, that says 300 nanometers. So really, really tiny hairs. Human hairs are thousands of nanometers, so much finer than your hair. Okay, so those two are two of the different ones. We have a third one, and this one is not included when they talk about van der Waals forces. Got to start off by saying they named it wrong. It is not bonding. They should never have called it bonding, but they did. We can't fight that. Okay? So this is going to only happen in very specific molecules with very specific atoms connected to each other. If you don't have these atoms connected to each other, you can't make this happen. So you either have to have hydrogen hooked to fluorine, hydrogen hooked to oxygen, or hydrogen hooked to nitrogen. Okay? If you have that, you're going to have some special properties for two reasons. One, F, O, and N are at the top right of the periodic table, where electronegativities are really high. So it's like dipole interaction, only stronger. It's about as strong a dipole interaction as you can make. But it's not just a dipole interaction, because it's got to be doing something different. So there must be something different about this. And the clue is that they didn't put chlorine on this list. Okay, well, why is that a clue? Well, chlorine has the same electronegativity as nitrogen. They're both 3.0. You look them up on the table. They got the same electronegativity. But nitrogen's on the list and chlorine's not. The difference is size. These atoms are small. And the smaller I make the atoms, the closer together I can get those molecules to each other. And if I get the molecules close to each other, they can stick together better. It's not hard to come up with an example of that. You just got to think about magnets. Some really strong magnets here. Actually, are really strong. So how come it's not sticking to the wall? Why isn't it sticking to the board? Not close enough. I got to get close enough for it to stick, right? So the closer I get, the more the magnetic field works, the better they stick together. Well, the same is true here. The closer together those charges get, the better they stick together. Okay? So the fact that they're small means they can get together close. If they can get together close, they can hang on to each other. Okay? Fact is, the reason why they call it a bond and they shouldn't is they kind of share with the lone pair next to them. That if I have hydrogen hooked to oxygen, whatever else that oxygen is hooked to, there's going to be a lone pair on that oxygen that a hydrogen from another atom can come up close to. So it's the hydrogen on this atom being attracted to the lone pair on that atom. Hydrogen in this molecule is attracted to the oxygen in the other molecule. And vice versa. This hydrogen would be attracted to that oxygen. This is by far the strongest of the intermolecular forces. But even as the strongest of the intermolecular forces, it's only 5% as strong as a real bond. A real bond is at least 20 times harder to break than an intermolecular force. So can anybody think of a molecule that has hydrogen hooked to oxygen? Water. So hydrogen hooked to oxygen for water. So this is the hydrogen bond. The hydrogen on this molecule is attracted to the lone pair on that molecule. It's intermolecular, between the molecules. And this is what keeps water from evaporating or boiling. Actually, water does this better than HF because water has more lone pair it could use. And it's got a couple of hydrogens it could do on this end. Okay? So it can a hydrogen bond all the way around. Turns out that water, on average, makes 2 hydrogen bonds. And that is what makes it stick together so well, is it's got the strongest intermolecular force, and it makes 2 of them. Okay, so hydrogen bonding. Hydrogen bonding is why you don't want to freeze water, you don't want to freeze a soda. Okay. Say, what? Well, why don't you want to freeze a soda? What? It explodes, right? Well, what's that got to do with hydrogen bonding? Well, hydrogen bonding has a direction. So it turns out that we got water. This one hydrogen bonds to this one. Maybe that made that bond too long. which can hydrogen bond to another oxygen on another water, which can hydrogen bond to an oxygen with another hydrogen. And if you draw it right, it turns out that, that in order to do that, you have to make hexagons. That's why in elementary school, every time somebody showed you a picture of a snowflake, it was six-sided. Or if you cut out snowflakes, they're always six-sided, because the crystal that water forms is a hexagon. And what's in the middle of that hexagon? What's in the middle here? It's the right answer. What's in the middle? Nothing. Nothing's in the middle. There's nothing in the middle, which means I had to make room for nothing. I had to move those water molecules apart in order to make that empty space. So water expands about 10% when you freeze it. Okay? Because it's got to make that empty space because the hydrogen bonds makes hexagons. Because they're directional. So you get hexagons with those hydrogen bonds. Those hexagons need extra space. It expands, and that's what destroys your soda can and sprays the stuff around the room. But it's also what tears down those mountains. Water goes into the cracks in the rocks, and then it freezes. It expands and makes the crack bigger. The next day it warms up, the water melts. It fills in the bottom of that crack, now it's wider. At night it freezes. Makes the crack bigger. And that's how you tear down a mountain range, is ice expanding and contracting. People in California complain about bad roads. We don't have the frost problems that the rest of the world has. In Michigan, I was riding a bus to college. I had to take a bus from one side of campus to the other. And I went into a pothole where the back wheels of the bus went into the pothole before the front wheels came out. Okay, huge pothole. Why? Because that ground underneath, the cement wasn't sealed. Water got in, tore it apart. Next water got in, washed that stuff away, made room for more water. Tore the next piece apart. And that's how you get potholes, is because of water freezing, thawing. Because hydrogen bonds moves them apart. So, how strong are intermolecular forces? Well, to compare them to each other. Dispersion forces are the weakest. And I'm gonna say this, so I just don't want you to be surprised. I'm going to call them, someplace along the line, I'm going to call them London dispersion forces. After a person, not the place. There was a chemist whose last name was London. Okay, so I'm going to call them London dispersion forces because that's how they are in my head. That's what I learned in high school. Your book just dropped the guy's name off the front of it. Okay, so dispersion forces, temporary, momentary, partial charges affecting the molecule next to them. Weak. Stronger, dipole interactions. Permanent charges are going to affect each other better than momentary charges. Strongest, hydrogen bond. I keep saying this, all much less than the real bonds. Because while it takes a lot of energy to boil water, it takes a lot more energy to take the hydrogen away from oxygen. You never do that when you boil water. Okay, so all things being equal, dispersion is weaker than dipole, which is weaker than hydrogen bonding. Okay. But you can get dispersion, there are things with dispersion forces that are solids. I can make it a big dispersion force. The way you make a big dispersion force is to get bigger molecules. Bigger molecules stick together better. The more polar it is, the more polar the molecule is, the bigger that electronegativity difference, the stronger the dipole, the stronger the force. So polar sticks together better, more polar sticks together more better. So that's how you compare them to each other. Now you have to decide which kind of molecules get which kind of intermolecular force. So what kind of molecules can have dispersion forces? Well, dispersion forces were caused by random motion of the electrons, right? So which kind of, so it takes electrons. What kind of molecules have electrons? Every molecule. So every molecule can do dispersion forces. But it's all nonpolar can do. So if it's nonpolar, you're only going to see dispersion forces. If it's polar, you're going to see dispersion forces and dipole interactions. So when we're trying to figure out whether something was polar or nonpolar, one of the things that's going to tell us is, well, it's how easy it is to melt or boil. Whether it's going to be a liquid in this room, a gas, or a solid. What kind of molecules can do dipole interactions? Well, the ones with two poles, which would be polar molecules. And a specific kind of polar molecule can do hydrogen bonding. So molecules with H attached to F or O or N. Not just have those same atoms in there, they actually have to be attached to them. Okay, to show you a couple of implications of that, or results of that, okay, let's talk about something you covered in okay, so last year, you talked about guanine. It was the G in CGAT, right? Adenine, guanine, thiamine, cytosine, right? So this is what a molecule of guanine looks like. Okay. And what I want you to notice is over here on this side, this is oxygen and hydrogen. This is, the blues are nitrogens. See, the blues have made 3, right? So if you look at how the electrons are, if you look at this, down here at this end, because nitrogen's negative, that it pulls the electrons away from the hydrogen, that hydrogen's positive. And that hydrogen's positive. And that this oxygen sticking out here is negative. Red's oxygen, blue's nitrogen. White's carbon. Right? So I've got a pattern of 2 positive ends and a negative end. And all of the DNA bases do this. So that if you look at the DNA bases and where the electrons are, there's our guanine. Everybody see this is what we were just talking about. Guanine let me pick pen. There we go. Guanine, notice it had the 2 positive areas and a negative area, right? If you look at cytosine, it's got an oxygen there, which makes it negative. It's got a nitrogen there that makes it negative. And it's got a positive here because you've got that hydrogen hooked on there. Notice how the positives and negatives line up. So the reason why C and G always went together in your DNA base pairs is because opposite charges pull them together. So that when you put, this is cytosine and thiamine, cytosine and thiamine. See, it's a different pattern. This one's got negative, positive, negative. Right? Negative, positive, negative. And this one's got positive, negative, positive. They line up. So A and T hang on to each other, but it's not permanent. It's just opposite charges. So you can pull them apart. Okay? And this is the C and the G. So this was the G. Come on, pen. So there's our, something that works. There's our positive, positive, negative, 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 positive. How they line up. Okay? If I try to put the wrong ones together, this is okay, that's okay. Those two will push each other apart. So C and G, or A and G will never go together. And that's how it self-organizes itself. You got one strand. When the next strand goes to put, there's only one that's going to fit next to C. There's only going to be one that fits next to G. There's only going to be one that fits next to A. So it's those shapes that make DNA work. Right? That's why we're talking about shape and polarity. Is it really is the underlying behind all a lot of chemistry. Okay? So the reason why your base pairs work. Okay. And this is just a simple graph. I'm going to graph hydrogen hooked to a bunch of compounds. And I'm going to do them by columns on the periodic table. So the first column I'm going to do is column 4A. So I've got CH4, then SI4, then GE4, then SNH4. Okay? Straight down the column. And what I got there is their boiling points. So that as I go down a column, the boiling point gets higher. Why? Well, if you look at these are all H4, right? So they're all tetrahedral. So they're all symmetrical. So they're all nonpolar. So these are all nonpolar. So the only type of intermolecular force they can do is dispersion forces. And tin does it better than CH4 because tin is doing those dispersion forces with 54 electrons, where carbon's doing it with 10. So that upward trend is all about dispersion forces. The bigger the molecule, the higher the boiling point, if it's only dispersion forces. Okay. Here's the next row. Here's the row next to it, group 5A. Okay. Group 5A, NH3, these are all trigonal pyramidal. These are all polar. So the difference between here and here is this has exactly the same number of electrons, so dispersion forces are the same. What's different is polar versus nonpolar. So this is the difference that dipole interaction makes. But if you go to here, if you follow this trend, NH3 should be down here, shouldn't it? If you're following the trend. But it's not, it's way up there instead. If it was just polar, NH3 would be here. But what else is NH3 doing? Well, NH3 has N hooked to H. It can hydrogen bond. So this gap here is about the hydrogen bond. So the gap between GE and AS is polar, GE is not. So it sticks together a little bit better. But NH3 doesn't stick together a little bit better, it sticks together a lot better because it can hydrogen bond. Looking at the halogens, row 7A. Row 7A is a lot like 5A. Got H hooked to Cl. It's not symmetrical. These are going to be polar. So this gap, again, is about being polar. But I expect HF to be down here, but it's not because HF has got hydrogen hooked to fluorine. So it can hydrogen bond. So hydrogen bond makes the big jump. And then you try the one in between, 6A. And in 6A, we get the same basic trend that you get a polar jump. But water's way up there. Why is water way up there? Because water can hydrogen bond 2 times. So you expect water to be here. If it could hydrogen bond, expect it to be there, but it's up here because it's got 2 hydrogen bonds. And 2 hydrogen bonds is going to stick together better than 1 hydrogen bond. So water, for such a tiny molecule, has a really high boiling point. Okay? So that makes it special. I got what? One last thing to show you? Nope, I'm going to run out of time. I have to do that when I come back on Wednesday. So, have a pleasant evening.